Okay, in this video I'm going to continue on with my tutorials on thermodynamics and statistical mechanics. This is video number 36 and I'm going to discuss the thermodynamic identity. I'd like to draw your attention to my website universityphysicstutorials.com. So this is number 2 of 2, or video 2 of 2 on the thermodynamic identity, because in this video I'm going to discuss diffusive equilibrium, and in video number 35 we discussed mechanical equilibrium. Now I'm just going to apply the techniques from video 35 here, which I did quite slowly. So if you don't understand what I'm doing here, just go back to video number 35. So we're talking about diffusive equilibrium. Okay, so before we even begin, you should understand that we're going to be talking about the chemical potential, because the chemical potential is what relates to the change of the number of particles. And the reason that is because the chemical potential is the amount of energy added to your system when you change or you add one particle to your system. So what we're going to do is, this time, just for convenience, and this is convenience only, we're going to say that there's no exchange in no exchange in volume. Of course we could generalize it to have an exchange in volume, but we'll be able to see that the argument is the exact same. So we only have an exchange of particles, and we have an exchange of energy only. Okay, and what we're going to have is two systems, just like we did in video number 5, two systems. So what we're going to do is bring two systems together and see what they do in order to come into diffusive equilibrium, so when there is no longer an exchange of particles between the two systems. So we know that equilibrium happens when the rate of change of the total entropy with respect to, we'll say, the energy in A is equal to 0. We know that, we've seen that numerous times at this stage. Or we can rewrite, which is also going to be the case, because we now are talking about exchange of particles, that del S total with respect to the number of particles in A also has to be 0. And this is at equilibrium. Okay, so that should make sense to you at this stage. So look, the usual tricks here, we know that del N sub A is equal to minus del N sub B. Okay, we know that del U sub A is equal to minus del U sub B. We know that. Alright, so look, we can plug all the things in as normal. What we're going to get, and that S total is equal to S sub A plus S sub B. That's a pretty important identity. Okay, so we're going to get del S sub A del U sub A is equal to del S sub B del U sub B, and this is at equilibrium. Okay, so we've seen that numerous times at this stage. But similarly, we're going to get a del S sub A del N sub A is equal to del S sub B del N sub B at equilibrium. So these are our equilibrium conditions. Now if we look at the units in this bad boy here, you find that the units are joules per Kelvin. Okay? The units of joules per Kelvin. But because the system is also in thermal equilibrium, it's in thermal equilibrium, so multiplying by temperature makes no difference. So we're going to be in equilibrium, so everything is going to be in equilibrium. So multiplying by constant isn't something that is a constant, doesn't matter. So if you multiply by T on both sides here, we're going to get rid of the per Kelvin, and we're just going to get this factor of joules. Alright, so by convention though, we multiply by a negative factor of temperature. So what that means is that we now say that minus T times del S sub A del N sub A is equal to minus T times del S sub B del N sub B. Alright? Now, this has units of joules, so we're talking about the joule here. And that's interesting. I always find that this is pretty interesting. Alright? So what we do is we define this as being the chemical potential. We define it by definition. We say the chemical potential is equal to minus T times del S del N at constant volume and constant energy. We call this the chemical potential. So this is the quantity which is pertaining, I suppose, to diffusive equilibrium. So when there are no longer an exchange of particles, we're talking, that's what equilibrium is, diffusive equilibrium, and we need to talk about the chemical potential. And we'll see later on that the chemical potential is the Gibbs free energy per particle, or is the energy added to the system when you add a single particle. Alright, so the larger that we have del S, del N, so that we'll say the larger that is, or the system with the larger del S, del N is going to want more particles because it has a smaller chemical potential. So when del S, del N is large, mu is small. So del S, del N goes up, mu goes down, or is smaller, we'll say. So the body with the larger del S, del N is going to want more particles. Okay, so finally, let's put it all together and get the overall thermodynamic identity. So in the previous video, what we saw is that the infinitesimal change in the internal energy could be written as the temperature times the change in entropy minus pressure times the change in volume. Okay, so this time, of course, we're going to follow the same argument. This time, entropy, okay, is a function of both internal energy, volume, and it's a function of temperature, or internal energy, volume, and the number of particles, of course. Okay, so that means therefore ds is equal to del S del U du plus del S del V dV plus del S del N dN. Plug in all of the bits and bobs that we have and rearrange to get du is equal to exactly what you'd expect it to be, TdS minus PdV plus mu dN. And this is the main thermodynamic identity. We'll be using this the whole time. You do this to derive the Gibbs factor, the Boltzmann, the Gibbs factor, the Boltzmann factor, and it's very important in quantum statistics, in phase changes and all that sort of things. So this is very important and very useful. Also, you can look up the Guggenheim scheme, by the way, if you want to remember all these. It's an interesting scheme. I may or may not do a video on it, but I remember when I was studying thermodynamics, that was the scheme that my professor had me using. Okay, so just remember that the chemical potential is the Gibbs free energy per particle. It's the energy which is added to the system by adding a single particle, and it is related to diffusive equilibrium. So the system which has a smaller, or the system, excuse me, which has a larger del S del N wants more particles because it is a smaller chemical potential. So thanks for watching. Please pass it on to your friends, subscribe to my channel, and you might also visit universityphysicstutorials.com. Thank you.